Welcome back, guys. As we said last week, part 2 of the Safety and Sight Across the Opti-Verse episode is going to be launched right now today. We really hope you enjoy the remainder of the conversation between Adri and Jason. It's just to jog your memory, we really spoke about the algorithms of the data handling in the control interlocking machine vision project. What we're now going to talk to is some of the results that Jason and Daron experienced in the project and some of the challenges they faced, and additionally, what happened next? What innovation are we doing next? So we really hope you enjoy the second special episode in part 2. And as always, catch us wherever you get your podcasts on.
And so let's talk about that integration a little bit more, because I know it also leads us to how do we know that this is going to continue working well in the future? So we essentially have given the algorithm permission where it's now sitting. And that permission is very narrow, very specific to what the algorithm can ask other equipment to do.
Yes, there's one thing it can do. Yeah. It can go and move the mud gun and close the tap holes. That's all it can do. And it can raise an alarm.
And so if it does this incorrectly, if the algorithm isn't working as it should, it incorrectly identified excess steam to the point where it wants to take this automated action. It's not necessarily a big deal in terms of safety and risk at that point. It's okay if we close those tap holes for a little bit.
Yeah.
The important thing is that the people are safe in the scenario. I know there's a business angle to this.
The business angle is very important. It's incredibly important, and it can't be put to the side because these guys have a job to do. They need to produce a certain amount of materials every day, and any interruption in that, unnecessary interruption, is not good. And so the algorithms acting on false positives is unacceptable, and it shouldn't. This machine vision algorithm is extremely robust because it uses this incredible neural network to identify steam in every image. And we count the number of identifications in every image at a certain frames per second. And then over a minute period, we keep track of how much steam has been generated over a minute. And so even if there has been a false positive in a single image, that gets smoothed out by all the other correct counting it's been doing.
So there's accuracy and speed in this.
Yeah, accuracy and speed comes
That's the
into
trade-off,
it.
right?
Yeah. But my point is that the algorithm is built in such a way that it actually doesn't produce false positives anymore. It's been an iterative process, and we can talk about that in a bit, but and this is one of the requirements of this, is it needs to identify dangerous conditions, but it should also not produce false positives.
Okay.
Because those two things are very important. It can't be an algorithm that identifies all the dangerous conditions, but then also have the same amount of false positives, because then that will just cause a lot of issues.
It's a high stakes game. Very narrow window to work within. Okay.
Yeah.
So, I mean, it sounds like a really cool algorithm. You said it's quite robust.
Yeah.
It's using an amazing network. It sounds like there were ways that we tested this. Is it running right now, real time, live?
It is running in real time.
In real life?
In real life,
Okay.
on 2 different sites. It's been implemented. We were working on a very specific site, and there were, news spreads, and there was interest in all sorts of other sites, and we managed to roll it out to a different site as well, making use of a lot of the infrastructure we built, and time transfer learning and all sorts of stuff like that. Running live on 2 sites on multiple tapping floors, looking at about 11 camera streams at the moment.
Wow. So it's running.
Yeah.
What do we need to do as a partner with this client, with arguably maybe the most important stakeholder, which is the operators, to ensure that, yeah, it's running, it's working. We've plugged it in, it's there. Is it recognized? Is it being used? Is it, I would use the word adopted.
Yeah.
Has it been successfully adopted by the people who actually need to make use of this?
I think it's an ongoing process, and different sites adopt things at different rates. And it's also quite a slow process. And the reason for that is these processes have been created and designed in a very specific way, and there's a lot of expert knowledge and historical knowledge that goes into managing and controlling these things. So bringing in a new technology can be quite challenging for good reason. You can't just bring in a new technology and it might mess up everything. So it needs to be taken with a pinch of salt, and it needs to be a process. So the first step of adoption for us was just to get the algorithm down and run, and we monitor its performance. And as we're monitoring the performance, we'll make adjustments and make sure that it's doing a good job. It's identifying dangerous conditions. It's not creating false positives. That's step one. The second step is then to put it in front of operators. We did that through the surveillance system at first and not touch the alarms for a bit, just so that it's there and they can see it. It's not shouting at them. There's no alarms going off that says, look at the screen. But just to get them...
There's some psychology here.
Yeah, no, definitely. Okay. And then they get familiar with it. And
soft landing. Okay.
Yeah, and then after that is alarms, where now the operator can get notified when he needs to look at the screen. And then finally, it's automated action. So automated action is also obviously quite a risky thing, because closing those tap holes isn't good. It's very much a no-no unless it's dangerous.
And so the business person upstairs.
Yeah,
sure.
But when you reach that point after taking all these steps, you have built so much confidence that you're at the point where you can actually have it do something.
You've also got this feedback loop of how well it's working on site with what I would again call the end users.
Yeah.
And so there's iteration in this process as well.
Yeah.
It's not like we built all these mechanisms from a layered video stream, alarms, automated intervention, all in one go. It wasn't this parcel that we packaged and delivered and made them install from the get-go.
Yeah.
It was an iterative process. And I'm assuming that through that period of time, we were able to ensure what we're calling a very robust model.
Correct, yeah.
Were there other factors that we needed to consider through this iteration? I mean, was this the only model we built? Because we're also saying this is live and it's in real time.
Yeah, so that's kind of the speed versus accuracy consideration. That was a challenge, because we couldn't just take the biggest and baddest algorithm out there, bad meaning a very accurate model, because the bigger the neural network becomes, the slower it runs, right?
Okay.
And our requirement
is intensive. Okay.
Yeah, and this thing had to run in real time. Not only in real time, it had to process a set number of frames per second for us to actually get good insights. And so we had to play between accuracy versus speed. And so we had to choose a very specific network that gave us the right type of accuracy as well as the speed. What was interesting, though, is that we did build a heavy and slow offline network, and we fed it the same data, and we did that for the purposes of validating the model. So if this network, this heavy thing that is very, very accurate, but it's quite slow, detected anything else that our quick but not so accurate, still accurate, very accurate, but didn't detect, then that is something that you can go and use to label and give to the faster network and train it again and then iterate like that. Constantly
validating the results of the live real-time model against very robust offline, can take as much time, and as much data as necessary, or input as
Yes.
necessary.
Yeah, and this is
And feed that
particularly important for true negatives.
Right.
So we had to find a feedback loop that says the algorithm didn't pick up excessive steam on this day or light steam on this day. And that is actually quite hard to come by because, again, operators aren't looking at the screen constantly. Nobody is actually seeing the steam necessarily because it is quite fleeting. And so it is important for us to have a feedback loop that can tell us, you missed these days, and make that part of the training set and retrain our live algorithm.
Okay. This was by no means a simple and straightforward process.
Yeah.
So we went
Definitely.
from, I remember you said in the beginning, part of our decision for this to be a real thing in happening in real time, we needed to go for something that could be lightweight and simple in its essence. But the road that we took was quite complex. We did actually end up with a second model offline that is very complex, very heavy. Were there any other challenges that you can think of? Pick one, because we're going to run out of time. Pick one. I know the adoption angle, I think, is one of them. We've spoken already about the speed and the accuracy, the trade-offs of this. Was there another challenge that we discovered along the way? Is all steam the same? Is a question that I would ask.
Yeah, there were many challenges, good challenges. I think another challenge that we faced was, I mentioned earlier that the process inherently has a lot of steam. You're working with water being put in contact with something like slag, and once they're put in contact, there's steam generation, and water being used to cool down things a lot, and that results in steam. So around the furnace, there are adjacent processes that often produce their own steam. And if it happens that the wind direction is correct, then the steam can be blown over our camera, and it might come across as steam from our system.
Okay.
So
that could create a false positive.
That can create a false positive. And we had to cater for this because it does happen. It's infrequent, but it does happen. And so this is actually a different classification that we had to add as part of our ensemble of things that we had to identify. What we called it wind steam.
Wind steam.
Wind steam. It's
windy.
It's steam that's being blown by wind.
Okay.
And there's probably a better term for this, but it looks quite different.
We'll ask the subject matter experts. They should leave a comment. Yeah.
Yeah, and so we had some interesting filtering techniques to remove that, and we were able to successfully detect those and, by extension, reduce our false positives significantly. I think wind steam was probably the biggest creation of false positives for us.
Okay, really important to get that out of the way.
Yes.
Blow it out of the way. Okay, that was really lame. All right, we don't have a lot of time left, so there's a lot more that we could talk about, but I want to bring it full circle.
Yeah.
I want to bring it back. So the goal of the project that we outlined with the clients was to deploy and integrate a machine vision algorithm for the purpose of lowering the risk or improving safety conditions within the furnace operations.
Yeah.
Did we succeed?
We did.
Great.
So
and we're done. No,
yeah, there was an incident that happened a couple of years ago that we've got caught in video footage, and we ran this event through our machine vision algorithm, and what we noticed was we were able to give a lead time of about 3 hours before the actual event happened, and that is quite significant. That means that 3 hours before the event, our machine vision algorithm would start complaining and saying there's something wrong. We need to put attention on this. And so there's 3 hours to make changes to the process such that it doesn't result in an event.
So that's that time question I asked you. How quickly can this incident occur?
Yeah.
Can it go from 0 seconds to 1? You're talking about 3 hours here. The operators had 3 hours to correct the situation, if I can say it like that. So the results we're looking for is lead times. That's what's indicating our success.
Yes.
Essentially.
Yeah. For example, if you had a lead time of about 1 second, that won't help because you can't even have the mud gun plug the hole in a second. So lead time is crucial. The more lead time you have, the better and more informed decision making you can apply. It's worth saying that just because you had a 3-hour lead time in one case doesn't mean you'll have a 3-hour lead time in all other cases. So
but
it's
you
still
will
very
have lead
important.
time.
Yeah, you will have lead time.
And so and that's also where that automated intervention of plugging the tap holes, closing the tap holes.
Yeah, plugging both tap holes. Yes, both. Yeah.
Be an engineer. That's where that comes in.
Yeah.
So maybe you don't have 3 hours to correct the situation. So regardless of the time it takes for an incident to occur, which we don't want to happen, and should this be a positive indicator that the algorithm picks up, it can do something about it in the most extreme sense. There is one decision it can make. It can turn the ship away from the iceberg.
Yes.
In enough time.
Pretty much, if you want to bring Titanic into the mix.
Yeah. I was thinking about Titanic and how there was so much lead time for these guys to turn the ship around.
Exactly. And so if the Titanic ship was too close to the iceberg and someone spotted it, but it takes a while to change the direction of the ship, right? So the same applies with a furnace.
Okay.
Yeah.
That's fantastic. Let's wrap this up. I have 2 more questions.
Okay.
No, I think I'll keep it to 1. I think we've spoken quite a lot about factors that contributed to the success of this. So if I had to ask you a question, my own, what was the cool factor? Was there something that came out of this project that we didn't foresee, we didn't expect it? Or as we were working through it, even though we knew it was there, it was actually just really cool to think about.
So maybe to touch on that, on something I mentioned earlier that I said we can touch on later, which was
brought it back around.
Yeah, we'll bring it back. We'll bring it back. So as part of this machine vision algorithm, we're detecting people, and that actually resulted in all sorts of other applications of using machine vision. The one that we've also taken forward and have implemented and is also running live is something we call exclusion zone detection. So I mentioned that the tapping floors often don't have physical barricades because you actually need people to
walk onto the floor.
Yeah, on occasion, but for the most part, there shouldn't be people. So another application of a machine vision algorithm like this that came kind of for free because we're detecting people is when a person, so you effectively draw a virtual barrier on your video footage. If a person enters that, then something happens. And the action in this case is don't have moving machinery in that area move, which makes sense, right? If a person is in an area where there could be moving machinery, rather have that piece of machinery interlock.
And this is machinery that you don't want to be around.
Exactly. So this is actually the mud gun. And so that's also been implemented and running live. Is if a person enters this area, then it makes sure that the mud gun isn't moving. It stands still. It also is integrated into alarm systems so that operators are also notified by it. So again, if someone moves into the area, the operator can look at the footage and see, okay, well, that person's supposed to be there because they're supposed to launch the tap hole or whatever the case may be. And that's okay. But if there's someone just hanging around that shouldn't be, they can also then take action. So
That's
that's pretty cool extension of our project.
I get the feeling you guys were quite chuffed that you sort of attached this element to the project as a whole.
Yeah.
Is there any other future work that we've been talking about with this particular client or with particular stakeholders on separate sites that we haven't been to yet?
So I think most sites want in. They all want their one,
Awesome.
and it's great because focus on safety is crucial.
Okay.
And I think they can also see the value they can bring to the table. So I think the same thing applied in different areas, different sites, important. But then there are also a number of other applications of machine vision that would have a similar type of impact. And there are stuff in the pipeline. I can't elaborate on it now, but yeah.
Okay, we've got our creative juices flowing.
Yes.
There's future podcasts, maybe.
Maybe future podcasts, yeah.
Okay. I think we should probably get one of those stakeholders into the podcast.
Okay.
Give us their perspective.
Yes.
Having worked with Optimum, having worked on this type of technology, actually sort of boots on the ground feedback. Okay, that would be fantastic. Well, thank you so much, Jason. Thank you for your time. Also, a special shout out to Duran Jaffe. He wasn't here with us today, but we know him as the Bright Spark. So thank you so much for all your work. And thank you to the listeners. So you can find this podcast anywhere where you listen to your podcasts. And thank you for taking your time on your daily walk in the park or at work or on the road going home. We really appreciate your time. Until next time.
Thank you.
Thank you.